Hello, everybody. Welcome back. In this lesson, we will go over an important technique of integration. Now, what are the techniques of integration? Now, before talking about techniques of integration, let's talk about techniques of differentiation because integration is closely related to differentiation theory. When you consider derivative computations, do you recall we had some rules of differentiation? First of all, we had linearity properties. And beyond that point, we had the product rule, the quotient rule, the chain rule. In fact, we pretended we treated them like formulas or like, let's say, rules in particular. Even if we call them, even if we treated them like rules, those are essentially giving us some techniques of preparing derivatives of complicated functions. So that is exactly what we need to identify in this journey of finding techniques of integration. However, since integration process is little sophisticated, it's a little complicated compared to differentiation process. We are trying to do it uh, one step at a time. In the level of calculus 1, you're going to see integration by substitution to reverse one of the rules of differentiation. However, when you consider the other rules, like let's say uh, the other collection of rules that we had in our toolbox, it will not be in the curriculum of Calculus 1. For instance, the reversal of the product rule will appear in Calculus 2 level as a topic called integration by parts. Here we are going to talk about integration by substitution, and there is a pet name for that. For integration by substitution, we call it U sub. That's a nickname. We will call it U sub because usually we use U in the position of a substitution. But now, where's the origin of this story? Look at this. The origin is none other than the chain rule. Do you see? This is the plain original chain rule differentiation formula. Now, if you reverse it, if you reverse this formula, if you integrate the right-hand side, you end up getting the left-hand side, and that's what you see here. Now, with that, what are you going to get when you do this process? Like, let's say, uh, how can you have this tool? Now, let's say this is the tool. Now, there are certain tools in mathematics. They're just tools for the sake of just being a tool. However, the practical usage is minimal. This is one such situation. You have a formula, but it's very hard to apply because the starting point of this application demands a lot. So the method that we are going to do, or the way that we are going to unfold this tool is to use it as an algorithm, or there's a method behind it. The way that we are going to do is, first of all, we need to recognize there's a composition in this case. The first thing that we are going to do is to recognize that inner function of that composition. We are going to name it like u equals gx. So this is going to be our u sub, and then convert the integral into new variable. Now let me briefly explain exactly the process in this situation right here. Once you have u equals gx, the next step, we will take the derivative of u. So du dx equals g prime x. However, we are not going to employ this particular form. We will convert it to the operator form of it, which is called du equals g prime x dx. You can pretend it like you're just cross multiplying by dx, but essentially it is not a cross multiplication. It is the operator form, which is a different uh, part of this conversation. However, I will just use it. Now, g prime dx, g prime x dx is appeared right here, and it is nothing other than just du. It's right here. And then don't forget you have u equals gx. Now, let me write down this entire integral in terms of this new variable. You have f prime u, gx is u from the substitution. And then g prime u is none other than just du from this formula, or the from that operator form. And now if you look at this very carefully, you're integrating a function f prime with respect to a new variable. Just it's just the original function evaluated at that particular input variable, then plus c. But don't forget that u is none other than just gx. If you replace it back, your answer will turn out to be just this right hand side. Now, that is exactly the method that we are going to use. Now, the problem in this particular account, this particular description is, now here I worked with this example, worked with this method in abstract sense. There are no descriptions for these functions, and you may be confused when you look at it in this way. Now, let me do this. Other than using this description, the way that I did this computational method, I will use it in an example and I will show you exactly how it's going to work. And then starting from that point, I will work with a bunch of problems. It will be essentially the same practice. But the key component, the key feature is this: recognizing the appropriate u sub is going to be the key component in all of them. Let's jump to the first example. Can you see a composition here? If you can see the composition, can you recognize the inner function of that composition? Then name it u. Take a moment. Right? So the first thing that I'm going to do, first of all, let me show you one thing. I will just open a box here because the derivative computations will be, it's not going to be a part of this computation. So I will write it separately. So u equals x square. That is the inner function of the computation. Then du equals the derivative of this, 2x, times dx, that is the operator form, 2x dx. That combo, the combination is right here, which is replaceable by du because there's an equation, it's an equality. So now I will change everything. This problem here is none other than 2x dx turns out to be just du times e to the x square is none other than e to the u. Now that gives us e to the u then plus c, because we know the answer of ex dx. So you know the answer for eu du, which will be just e to the u du. Now don't leave the answer like this even if you're done with the integration process. Now here you're done with the integration process because there is no integral anymore. You found the answer. But do not leave the answer in terms of u. Replace it back to the original variable because we are the ones who introduced this variable u. It is like translating this problem, the original problem, to a new language, the language of u, and then giving the answer in terms of that new language. Nobody will be able to understand what it means unless they are fluent with this new language. So you need to convert it back to the original variable before presenting the answer. So e to the u is none other than x squared and then plus c. So let's have this practice now. Do you see? It's that simple. Let's use it in a few examples. In this example, now here, let me do this. I'll use the derivative right here and I will continue with the problem right here. So what is a u sub? If you don't see it at once, think about it. which function is the base of that composition? What is the inner function of the composition? If you look at it very carefully, you can see that is sine x. The outer function is the power function to the fourth, right? So du equals cosine x dx. Cosine x dx combination is right there, which can be replaced by du, and then sine x happen to be just u, and sine to the fourth is going to be u to the fourth. So now simplify, and this is going to be u to the 5 over 5, then plus c. And then don't leave the answer in that form. Convert it back to the original function. Sine to the 5 by 5 plus c. It's that simple when you understand the process. The next step. Now here, take a moment. Take a few minutes to work with this problem on your own. Pause the video and give it a try. And then let's come back. What is our u sub? The composition, the base of the composition is x squared plus 1. You can have just x squared, but it's not going to facilitate too much in the long run. So x squared plus 1. Du equals 2x, and then this will disappear, and then don't forget dx. And then the only problem is here you have x dx, but here you have 2x dx. Now what are we going to do? At this point, you need to divide both sides by 2 to get 1/2 du, which is equal to x dx. X dx is none other than 1/2 du. So this will give you just 1/2 du. This is a constant multiple. Don't forget, you can bring it out. And then this component has just u to the 10. Now the integral right here, it becomes 1/2 the integral of u to the 10 du. You know how to perform the integral of u to the 10, which is u to the 11 over 11 plus c. You can combine these two constants if you like, and that means 1 over 22, 1/22. So that's going to be then u to the 11th is none other than the 11th power of x squared plus 1. Let's proceed to an example, one more example. Now, sometimes you may need to do some simplifications. Now here, the connection, when you need to play with these terms, you may see some connection. Sometimes it could be tricky. We did simplifications in integration. Sometimes simplifications can be performed even when you work with, and even when you're working with some u sub problems. So it can appear anywhere. So this is one such situation. First of all, try to recall the derivative of tangent is going to be secant square. Since I'm not seeing anything right away, I'm going to just do this and see whether I can just maneuver this problem somehow towards this scenario. So du is going to be secant square x dx. I have 4 copies of secant square here. However, if I had only 2 copies instead, then I do have a nice replacement for one part. Now, how am I going to work with this? So I'm going to have tan to the 4th. So that is already, without just converting this one right away to u, now let's try to clean this up a little bit. Tan to the 4th, which is not going to be a troublemaker because it's already pretty much like our substitution. And then secant square Secant to the fourth can be broken into two pieces, secant square and secant square. Now, when you do that, can you see one of the combinations, one of them will form our du, but there is an extra. What are we going to do with this extra? That's exactly when you need to recall little bit of trigonometry. Actually, we have seen this again multiple times, and this is very useful. Secant square x is none other than 1 plus tan square x. That is exactly a result of the Pythagorean identity, right? It is a variation of Pythagorean identity. So let's do this. Tangent to the fourth. Secant square is none other than 1 plus tan squared x, and then secant squared x dx. Here, this entire process is just to brush it up a little bit so that you can see it better. Now look at this. In the next step, I'm going to convert everything to u. U to the 4 times 1 plus u square times secant square x dx is none other than du. So it's going to be u to the fourth du plus. Now here, if you have a struggle in this step, like let's say once you have this integral, how do you perform that? You cannot take the integrals of both pieces and then just combine them. There is no product rule for integration. At least there is no product rule for differentiation that works right away as the product of each derivative. So there is no expectation for that in this scenario. What are we going to do is to distribute this, and then it becomes a polynomial. U to the 4 plus u to the 4 times u to the 2, so it's u6 times du. Now here, when you integrate, you will end up getting each component by the power rule. So u to the 5 over 5 plus u to the 6 over 6, then u to the 7 over 7, I'm sorry. Well, updated u to the 7 by 7, and then plus c. Don't forget that plus c always, that should appear at the end. And then don't forget our u, the original variable, is none other than just tangent. So tangent to the 5, again tangent to the 7, all right, so that is our answer. Now let's proceed to another example. What are we going to do in this scenario? The only obstacle here is to have a complicated term sitting inside a square root. So how are we going to deal with it? Now think about this. This doesn't offer much, but what you can see is the inner function right away. And if you take the derivative, that turns out to be just a constant, right? The derivative of 6x is going to be 6 times then dx, of course. And with that, you can change this integral, right? Integration is now integral of square root of u, because u itself is right here. And then du is none other than, right, dx happened to be just 1/6 of du. 1/6 of du. So now this is none other than just a square root. That's a square root as the power, and 1/6 come to the front. And now 1/6 u to the 3/2 divided by 3/2 plus c. There are simplifications that you can do here. You can flip and multiply. I'm not going to explain exactly the simplification, but figure it out. Just algebra. then plus c. Example number 6. Can you recognize the appropriate USAP? Sometimes it is not just about just looking at a very complicated interior function of a composition. That sometimes it could be just the position it is located at. The position itself is the interior of that function, the composition. So in this case, now pause it and try to recognize it. Give it a try. If you do not see it, then you can continue watching it. All right. So pause it and have a quick thinking about it. All right. I hope you gave it a try. And now I will recognize it. It's just the function in the denominator that is exactly the composition of this function and just 1 over x. When you feed this function into 1 over x, that becomes just 1 over x squared plus 1. So that's why it works in that way. Take the derivative 2x dx. We have 2x dx, but we need 3x dx. It is just a constant multiple that you need to play with. So I will divide both sides by 2. And then a replacement of x dx is right here, x dx. So now with that, don't forget 3 is separated. X dx is none other than 1/2 du. And then I have 1 over u. Simplify 3/2 1 over u du. Ln of absolute value of u plus c. That's the integral of 1 over u. Now, what is this? Ln of absolute value of x squared plus 1. Of course, don't forget this. X squared plus 1 absolute value of x squared plus 1. In fact, like absolute value is redundant in this case because x squared plus 1 is already non-negative, but it never hurts if you have additional absolute value unremoved in an answer. All right, so the last example. What are we going to do in this situation? In the previous example, we recognized the denominator as our substitution. Now, here also, if you try to think about the same line of thinking, right? So it's not going to work because if you consider like, let's say u equals x, if you have a substitution called u equals x, that simply means you didn't change anything in the problem. You just write it in terms of like, other than having u, other than having x, you're going to have u. That doesn't make sense. So other than having this, now it is not about recognizing the function in the denominator. Sometimes it's recognizing exactly these moving parts in the composition. Pause for a moment. Try to recognize the u sub. You need to balance two things. You need to recognize the u sub and you need to work with the derivative and see whether those two would match with each other. All right, I hope you gave a try and let's see. I will consider ln of x in this scenario as my u, right? So du is going to be 1 over x dx. And look at this, 1 over x dx is exactly what you see here, dx, and there is a x in the denominator. So that component, this component is none other than just du. And then you have just this one in the numerator, it happens to be just u. The answer is very simple at this point. You need to integrate u to the 1. So just use the power rule. U squared divided by 2 plus c. And that turns out to be the square of u, ln x complete square divided by 2, then plus c. And that's our answer. So with that, we conclude this lesson on substitution, the method of substitution. This is the first technique of integration that we learn in calculus, which is essentially the reverse of the chain rule that we used in differentiation. However, the process is going through a simple method called, uh, which has a nickname of U sub, but recognizing the corresponding substitution can be challenging sometimes. At the same time, recognizing a given problem is on the proper path of a U sub or not is essential as well. Not all problems can be handled by using a U sub. Sometimes you need to recognize whether it is appropriate to use this method or not. So that is exactly when you need to have more practice to work with these U sub problems to see whether it's meaningful or not in a given problem. So with that, we will conclude this lesson, and we will meet in the next part of our conversation. And please make sure to have some practice problems, work with practice problem sets, and have enough practice, and check the textbook and see whether you can have some extra problems. There are plenty of problems. I did not specify them because I gave a fair sample of problems here illustrated. So I hope you have a good practice. You will get a good practice and understand this concept, grasp these concepts better, so that you can have them injected to your muscle memory. All right, so I will see you in next lesson. Have a wonderful time with these problem solving sessions, and enjoy problem solving.